Welcome to Group 13's project, the GPS Targeting Pod, also deemed Project Scorpion, presented by Angelo Elise, Jacob Baker, Ava Perone, Rostislav Raviv, and William Yerkes. The goals of the GPS Targeting Pod are to determine the GPS coordinates of foreign targets at a distance, calculate the trajectory using a GPS module, a magnometer, which is a digital compass, a gyroscope to determine angle of the device, and a laser rangefinder to determine distance, and ultimately protect soldiers from danger. In turn, protecting the lives of our troops overseas.
Hi, my name is Ava Perone, and my major is computer science. The functionality requirements lay out the specific capabilities that the product must have at completion. There are 10 requirements for the GPS and targeting pod. The first is that the solution must be able to display read data on the user's screen. For example, the GPS coordinates. Drive based on the communication data from the controller. The device must be able to move based on the input from the joysticks on the controller. Determine bearing using the magnometer and read the angle using the gyroscope. The device uses these values to figure out the bearing or position of the tank, which is then used in an equation to find the location of a target. Read the distance with a rangefinder. The device uses a laser rangefinder to retrieve the distance of a target. It is then used to calculate the GPS coordinates of the target. Calculate GPS location. Like I said, once you've retrieved all the data, you can put all of it into an equation and figure out the GPS coordinates of a target. Gather the video data. The device uses a USB camera to stream live video from the tank to the controller. This allows the user to know where the tank is pointing, where the laser is pointing when they're using it. Communicate one-to-one with the controller. The tank communicates with the controller using TCP and UDP protocols, which allow the transfer of data. Read input data from multiple analog buttons. The buttons are used to change the position of the laser by moving servo motors. Read input for joysticks. This data is used to move the DC motors and steer the tank.
The usability requirements ensures convenience and simplicity for the user. The GPS targeting pod is controlled from a distance, allowing the user to control the motor's operation, steering, and speed of the vehicle. The targeting pod, designed to deliver power effectively and efficiently through all the components and sensors to increase the battery life. The targeting pod also communicates wirelessly with the controller and allow data transferring and ease of operation for the user, where the user can track any movements and sensor readings from the field. Video data is simply streaming from the camera on the targeting pod to the display on the remote controller.
Our safety requirements were pretty simple. Mostly the wiring. That was the main issue. We had to make sure that the wires were not exposed to other components that may cause a shortage. As far as the battery supply and voltage input, we had to make sure that certain components required 3.3 volts or 5 volts.
The structural team was tasked with operating within 3 constraints, the first of which was the positioning of components. Our project sponsors specified where certain components, such as the laser, IMU, and GPS antenna, were to be located and mounted. The second, functional design. The design of the system was to be functional both in terms of fabrication and operation. And lastly, tensile strength. The forces generated from the motors was taken into consideration, and it was determined that some areas must be stronger than others in order to maintain structural integrity.
The constraints set upon the battery management team were as follows. Provide ample wattage to the system for both the controller and the tank so that all modules can run at effective power levels. Have an ample runtime so that both the tank and the controller again could run for an extended period of time until the mission is completed. Communicate battery voltage values back to the main computer so that the user could have an understanding of the situation surrounding the tank itself and know how much time could be left down to the minute. And have protection for fault scenarios so that if there ever was an instance of a problem or fault arising within the tank or the controller, both devices would be able to alert the user and proper precautions and actions could be taken.
Some of the hardware constraints in the development, such as cost, availability, power requirements, made us choose devices and components very carefully. For instance, almost all the modules except for the laser and the DC motors operates on voltages between 3.3 volts to 6 volts, which ensures efficient power supply with less need for DC converters or DC regulators that will just increase the inefficiency and produce more heat. The motors were chosen to have high torque with minimum current draw. The GPS accuracy is up to 50 feet margin of error, which is very precise and important due to the importance of the application in the terrain. And the central processor is the new Jetson Nano module, a quad-core ARM processor to process efficiently and fast video data.
As far as software constraints, we did not have a lot of time. Most of our teammates were doing internships, doing ED1. However, there was some programming going on during that time, but not a lot because we needed to physically be there to brainstorm and gather ideas. However, when ED2 came in, mid-September, everyone was back from their internships. We were able to start programming the modules. However, along with programming the modules, we found out there were certain components that were better than others. So there was a lot of changing between the code, having to use different libraries, and having to do research on how to use those components. So now the CPU costs, it was pretty heavy as we were sending a lot of data between the Jetson Nano and the Raspberry Pi, as well as displaying information on the camera on the Raspberry Pi from the Jetson Nano. The memory, not so much. Security, type of security we were using was TCP, which is far more secure than UDP. That allows us to send that packets and confirm those packets into the other microcontroller, in this case, the Raspberry Pi. The controller design is pretty simple. We have two joysticks connected to the analog to digital converter and buttons connected directly to the Raspberry Pi GPIO pins. And the Raspberry Pi has a display which shows the camera of the tank, and the router is basically our gateway to be able to communicate with the Jetson Nano and the Raspberry Pi. The two joysticks allows us to move the tank, and the buttons allows us to interact and move the servo motors, as well turn on the laser with just a simple switch. With the buttons and joysticks, they do not work simultaneously. So what we have for the joysticks is once you start moving and you're able to pick the target, you turn on the laser with one of the buttons. You would press 2 buttons on the connectors, and that will be able to activate the servo motor. So that allows you to move the camera as well as the laser to find your target.
The tank includes a wide-angle camera in front of it to get a wide view of the field, a GPS sensor to provide an accurate coordinates of the tank at any given time, an MPU module that includes magnetometer, accelerometer, and gyroscope for velocity and magnetic field measurements around the tank, a laser rangefinder to measure the distances of objects or targets from far away, a PWM module, and a motor controller to control directions and the speed of the tank, 2 servo motors to control the horizontal and the vertical angles of the laser and the camera mounted on it. In addition to this, on our proof of concept, a small router was added on top of the tank to provide local wireless communication with the controller.
The structural components of the project were comprised of both the tank chassis and the controller housing. Now, both of these are responsible for housing the components of their respective systems. The structural implementation for both the tank chassis as well as the controller housing consisted of coordinating with other subsystem leaders in order to ensure that enough space would be available to house the necessary components.
The battery implementation went as follows. Pictured on the left is the battery stack, 4 batteries in series for a total of 12 to 16.8 volts. Then, through operational amplifiers, differential voltages were taken across both the top and the bottom of each individual battery, thus outputting the individual battery's voltage. These values were then converted back to digital data through an analog digital converter into a microcontroller, which is pictured in the center, which then output digital signals back to the picture on the right through optocouples for shunting of the batteries in the condition that one of the batteries in the stack was of a differing voltage from the rest. It would then shunt the batteries that were higher, until they were all equal once again, thus improving the lifespan of the battery stack itself. Pictured on the right, we have a barrel jack for charging, a buck converter for powering the microcontroller, low side switches for charging and discharging, and operational amplifier comparator flags for determining maximum charge and maximum discharge. After doing multiple design reviews with both our sponsor and an additional outside person, Perry Weinthal and Lin Dang, the design was confirmed to be correct and would be operational. Following these design reviews, the layout section began, where I began to lay out the traces for each individual component. Picture below, left to right, are the front and bottom layers of the PCB battery management board for the tank. After following all the traces and running everything how they were supposed to, I then underwent another design review with both Perry and Lin until the design was once again confirmed, and then I ordered the boards from JLC PCB. When the boards arrived, I then populated them myself by first stenciling solder paste on each pad, placing components individually, and putting all the boards through a large reflow oven to solder them down accordingly.
Not much to talk about the embedded hardware implementation. As you can see here is just a GPIO pin layout of our modules. Not much.
Software implementation. When implementing your code and programming, you have to program each component separately so that you make sure that everything works by itself. Then you one by one put them together. And since we used multiprocessing, we've used the items that were going to be in the same process. we put those together and we tested those separately. Then once we were done with that, we did the multiprocessing and we tested them all at the same time. And this all includes trial and error. And then at the end, we integrated all the code together. We put 3 different processes that we had, and we ran them all at the same time.
Throughout the process of designing and fabricating the tank chassis and controller housing, a lot of testing was necessary to verify that the measurements and spacing of the designs and the prints themselves were actually accurate. That being said, a crucial part of the tank, the tread system, presented many issues after they were attached. The problem that was faced was one of the shafts on one of the repurposed motors seemed to be a little crooked, which caused a less than ideal rotation. After testing many possible ways to fix this and considering getting a new DC motor, the best possible solution was, we determined that the best possible solution was to continue working with the repurposed motor and to simply reposition the motor, wheels, and tensioner to create a functional tread. And also testing and design changes and also reprinting was performed on the controller housing. As can be seen in the middle photo, the spacing of the controller component mounts had to be precise so that the individual components could be securely attached to the housing itself. Throughout the process of testing, the testing basically verified that the components were not detached during operation. And lastly, the pan and tilt system of the laser mount was difficult to calibrate because of the many moving parts. However, after some time and many adjustments, the laser mount was positioned in such a way that it was not only secure, but also capable of moving within its full range of motion.
In order to make sure that all the battery boards were operating as specified, I then went and put 4 batteries in each board individually, inserted and programmed a microcontroller with a test program, and hooked up oscilloscope probes to ensure that all boards were operating logically as they were supposed to. I found that all analog data was as specified and expected, all digital inputs and outputs read and wrote as expected, and the boards were in full functioning operation.
Testing hardware is very important for minimizing costs and saving time on fixes later on. There are multiple ways to test hardware designs, such as simulations, using oscilloscopes, physical breadboard testing, and even software if using a microprocessor such as Arduino, as we can see in the picture. Our design was tested on a breadboard and an Arduino IDE to measure the voltages on the pins. The board we see in the design measures the voltage levels of all the 16 batteries on the tank to show the user the state of the battery.
Software testing. Like I said in the last section with implementation, that we used multiprocessing and we tested each component separately. So in the first picture, you can see I'm checking the CPU utilization as we're using multiprocessing to make sure that we get the best and most effective results. Then in the second picture, you can see I'm testing a singular module, the camera. And once we had completed that, we were able to test the camera and the GPS at the same time, which is the coordinates that you see at the bottom of the center picture. Then in the third picture, you can see we have 2 processes working together here, the camera and the magnometer. You can see the angles change, and you can see at the bottom it says the number of packages, which signifies that the camera frame is being sent.